So we're looking at indices or powers, and we'll start off by looking at the basic rules before we do any examples. About 5 or 6 rules for indices, and I'm sure a lot of you have seen all these rules before, or at least some of them anyway. So rules of indices. Okay, so first rule. You have xn, xm, and this together, x power n plus m. Yeah. And we'll look at the proof of this. So xn times xm, that's equal to x multiplied by itself n times. And xm is x multiplied by itself m times. So obviously it doesn't require much imagination to see that the number of x's you have here is n plus m times. So it's a fairly obvious rule really, and that's our first rule. So if you can write this down please. The heck? That's equal to xn plus n then. Okay. The next rule. So xn over xm. And that's equal to xn minus m. Yeah. So the proof here for this one, xn over xm, yeah, you have n of them on the top and m on the bottom. So there's n here, and then at the bottom there's m here. But the thing you can do with this is you can cancel them. So we can cancel 1 by 1. Cancel 1 by 1. So each time that you cancel, you lose an x on the top. How many times do we lose an x on the top? We lose an x on the top m times. So you're left with x dot 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 n minus m. So that's x power n minus m. Okay, so if you can write that one down, we'll have a look at rule 3 now. That's rule 2. Okay, rule 3 I do next is xn m, and that's equal to x n m, like that. So let's have a look at the proof for this one. So the proof here, xn m, that would equal xn, 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 dot, 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 xn, m times. Because that's what it means to be power m. But by using the first rule, we can say this is xn plus n plus n, n. And if you add the number n to itself m times, then that's the same as just multiplying it by m. So that's the end of the proof for that one. So if you can write that one down, we'll have a look at rule 4 now. So rule 4, I think I'll do, what will I do next? Maybe I'll do fraction power. So x power 1 over n is equal to the nth root of x. Okay, let's look at the proof of this one. Got this, guys? Okay, continuing. So, the proof of this one, what I'll do to begin with is put power n on both sides. Now, if you use rule 3, so rule 3 would make this, 1 over n times n. Now this, so that's using rule 3, this is equal to x by definition. You know, if you have the square root of x and square it, you must have x, because that's what it means to get the square root. If you have the cube root of x and you cube it, you must get x, because again that's what it means to be the cube root. So by definition, if you get the nth root of x and you power n it, you must get x. On the left this will be x1, and on the right this is x, and that's obviously true, so that ends the proof of that one. So the proofs become a little bit easier as you have more rules that you can use previously. Okay, so the fifth one, I think we'll do minus power now. So x power minus 1 over n, that's equal to 1 over xn, yeah. Okay, can I scroll down a little bit? Okay, so proof. Proof's a little bit easier actually if I call that the 6th rule and then make this the 5th rule. So I'll just do a little bit of renumbering. The 5th rule isn't really it's not really a rule, it's more a definition. The first one is, if you have if you have anything to the power of 0, you get 1. Yeah. And then the other rule, I guess you could kind of call it a rule, is if you have 1 to the power of anything, that's always 1. Okay. So if I use that, it'll be helpful in the proof of number, that's 6, yeah, and that's 5. So x power minus n, that's equal to x power 0 minus n. That's equal to x0 over xn, and that's just me using the second rule. And then that's equal to 1 over xn, and that's me using the 5th rule. And the last thing just to say is, what about the situation when it's 0 power 0? So if we were to look at the first point here, we might say, well, it's power 0, so that means it should equal 1. Okay. But then if you look here, you might say, well, it's 0. So 0 times itself should always be 0. You know, if you think about it like this, if I have 0 power x, really we can only expect one number here, 0. Multiplying 0 by itself, regardless of the number of times, should be 0. But it leaves us with a bit of a problem with 0 power 0. Because if you think about it through this point of view, you might say, well, it's power 0, so that's 1. But if you think about it through this point of view, you might say, well, it's a 0 here, so it should always be 0 here. So it's actually, no, undefined, yeah, has no value. Now, in some situations you can make it have the value of 1, it's very special situations, but as a definition it is undefined. With some situations you can make it 1, but if you were to type it in on your calculator, I would suspect you should get an undefined error. Give it a try and see. 0 power 0. Syntax error? Math error? What do you get? Math error, yeah. Yeah. Undefined. Graphing calculator agrees, Mo? Yes. Yep. Alright, let's continue now. So, let's have a look at some examples. Example 1. So, just some simple examples to get started. We'll say x6 over x4. What does that simplify to? Well, that's x6 minus 4, yeah, which is x squared. So a simple example to get started. Okay, example 2. A little harder now. So suppose I have square root 4 square root 16 over 32 fifth root. That's a 5 now. 5 fifth root 32. So before I start this one, I'll just say that there are actually many paths you can take here, okay? It's not like, oh, there's only one way to do this one. It's actually a few ways to do this one. So when I look at this, you might say, well, perhaps first I want to do something about the 4 and the 32, because I can simplify that. Or perhaps you might want to say, well, I can do something with the root 16, because we know the root 16. It really doesn't matter. I think what I'll do is, I will do something about the root 16 first. So this will be square root 4 times 4 over 32 fifth root of 32. Okay, well, on the top, again, I can decide now, do I want to look at the top, or do I want to look at the bottom? So I think what I'll do is, I'll just do something about the 32.
Take out the 4.
4 by 4, and also I could cancel.
Yeah, 4 over 9.
It's 16 over 32, which is a half, so maybe I'll just do that next, actually. 16 over 32, fifth root of 32.
But 32 is still...
Yeah, I know, I said that. I said 16 over 32 is a half, I know it is.
No, it's not 32. 32 by 2. What?
Oh my goodness. Stop talking and just tell me if what I write down is right or wrong. So 1 over 2, fifth root of 32. Does anyone have a problem with that? No, good. Good. Right. So, next what I'll do, now I'll do something about the fifth root of 32. So to help me see what that is, I realised that 32 is actually 2 power 5.
That's what I'm telling you.
I know, one step at a time, So now, the fifth root of 2 power 5 is 2, yes. So, this is 1 over square root, it's 1 over 2 by 2, which is root 1 over 4. Yeah, now which can be written as root 1 over root 4, which is obviously 1 over 2, or 2 minus 1. So, this is the simplest I can make it. Okay, so write this example down. Adds a little bit, you know. Okay, you writing this down now? Do another example now. Okay, next example. Yeah. Example 3. So this one's a little bit harder because there's no numbers in it. Square root x, fifth root of x minus 5 over x power minus 5, fifth root of x power 5. Now I think what I'll do, for me, the first thing I'll do...
Take the x minus 5 up and the relative.
Well,
That down and that up.
if I look here, I have an x
6.
and I have an x minus 5. I could do something with that in a moment. And also, because these are both fifth roots, you see here?
Just cancel.
No, not quite cancel. Combine them.
Combine them.
So I can make it a single fifth root of x minus 5 over x5. Now that's good because in both cases...
1 over x.
Yeah.
Relax, please.
Yeah. Take it easy, man. Take it easy. Right. Listen. So here, these two are being divided. So what rule can I use? Which number? 2. And these two are being divided, so I'll use 2 again. So just be careful now, because this will be x1 minus 5. And then this is fifth root x minus 5 minus 5. So this is root x6, fifth root x minus 10. Right, we still have a little bit to go. So this one here will be square root x6, x minus 10, power a fifth, by using rule 4. So this is square root x6, x minus 2, by using rule 3. So this is square root x6 minus 2 by using rule 1, which is square root x4, which is x4 to the half, by using rule 4, which is x squared in the end. Now, yes, you can do this other ways. This isn't the only path to take. Okay, you can group them differently at the start. You should end up with x squared at the end. Okay, so write this example down. Mahmoud, HS1. Mahmoud, Gafar, Amjad, Zara, no H, Mo, Daniel, Sevi, there you are, okay. Sabrina of HS1, Alfreda, Aria, Chiadi, Yupeng, Amna, there, Mariam. Oh yeah, that's right. Sorry, Yupeng, could I just mark Mariam here? All right, HS2, Michelle, Abir, Autumn, there, Celine. Oh, sorry, use it again. Celine is absent. And Sophia as well, you say. Okay. Mubarak. Chidera. Mohamed.
Here.
Yep. Sabrina. Yep. Moza. Angela. Ahmad. Zara with a H. Alright, so I'm missing 3 people now. I think that's been the biggest absence now since we started. Okay, did you write this one down? Yeah? Right, next one. This one here, I just want you to expand and simplify a little bit into powers. So on the top, that would be 1 plus 3x plus 3x squared plus x cubed over x squared, which would be 1 over x squared plus 3x over x squared plus 3x squared over x squared plus x cubed over x squared, which is x minus 2 plus 3x minus 1 plus 3x 0 plus x 1, if you were to write it out as a series of x's. That was my question. My question was to, I guess you could say, write as a... Does anybody know what this form is called?
Is this quadratic?
Not quite, because quadratic,
Rational?
positive 2. These,
Rational?
no.
Progression.
Yeah, let's try the obvious one. Standard, universal, default, normal. Yeah, it's true. It is in ascending powers, no?
Isn't 3x 0, 3?
It is, yeah, but I wanted this form with the x's.
Isn't it ascending from minus 2 to 1?
It is, but what's the name of this form? Form 0.
Ascending values of x.
The ascending normalized default form,
Universal.
form 0, universalized. No. Harvard. Yes, alright, okay. Nobody knows.
Polynomial.
Polynomial. Nobody told me this. Yeah.
Please, how do we multiply 1 plus...
Listen, I can't hear him.
How do we multiply 1 plus x raised to 3?
Pascal's triangle.
That's how you did that?
Yeah. Pascal, third row, 1, 3, 3, 1. Yeah. Okay. Write this down, please. Okay. Got that? Not yet? Over here, we got it? Not Amjad? Yeah.
Is it compulsory that we must keep the powers?
Maybe not the x0 and the x1, but I put them in to emphasize that it's in polynomial form. Polynomial form is where you have it's a form like this. Let's squeeze it over here. It's where you have coefficients and x's with powers. So I'm just emphasizing the fact that it's in this form. Okay, can I scroll down? Yeah. Right, so the next thing we have to look at is a very particular special power, or special constant here. E. Now, this is on your calculator. It's a constant like pi. It has a fixed value in maths. something like this, roughly. I think your calculator says the same. This here, huh?
But did you do that from your head?
That's not up my sleeve. Yes.
What to do with your head?
You're right.
I didn't know what you did with
I'm a maths teacher. That's how. Right. True story.
like, I'm trying to do this, I just
It's on your calculator. Can everybody take a moment to find where this constant is on your calculator? You found it? Does your graphing calculator go any further? Where does it stop? On E? Well, tell me what's after the last 4 or 5.
Oh, no. It just shows the. I thought you meant the power.
Oh, yeah.
But it just shows the 8 to 8.
It's a shame.
Yeah. 45904.
Did you just Google to see if I was right? It's a total lack of trust in this class. Total lack of trust. Right. Anyways, so we'll see later. We'll see later why this is important. But what we'll want to do right now, just to practice, I want you to take out your calculator and just tell me what something like this is. E power 0.5, for example. What do we get here for this? Give it 3 significant figures. What's that? 1.65. Okay. And what about something like E minus 1? What's that? It's like 0.23 or something? 0.37. Okay. Yeah? So, what I want to have a look at now is what does the graph look like? So, if you want to graph something like y equals ex, what does that look like? Let's scroll down a bit here. I have a feeling that you've all seen a graph like this before. So x, y, it's very flat out here, and then goes like this here. Yeah, exponential, yeah. In fact, we know exactly what this number is here. What is it?
Value of that's 1.
Yeah.
Why is here?
Yeah. No. No. What's this number here?
E to the power. 1.
Yeah, 1. Guys, do you see this? Yeah, because it's x is 0. Yeah. Now what you did was you put in the value of 1. So here is 2.7. Yeah. Okay. So what we want to have a look at is just 4 different versions of this graph, because this one is a little bit too simple. Often our exponentials are of this form. A constant e and a constant x. And the nature of a and b will determine the shape, particularly if the a and b, if they're positive or negative. Okay, so let's have a look at the 4 situations. So I'll just split this in 4 here. So, actually, let me look here. Where's my pen gone? Can't see. Here we go. Actually, let me just make a little bit of a space in the center here. So what we're looking at is... Oops, hang on, get my pen back. We're looking at A, E, B, X graph. Y equals... Suppose that's the y equals A, E, B, X. So in the first situation is if A is a positive and B is positive, then we'll do if A is negative and B is positive, then we'll do if A is positive and B is negative, and then the last one we'll do is A is negative and B is negative. Okay, so let me just see, we'll put it in green here. In the exam, this is a common enough question. They'll ask you for a quick sketch. So you can do this quite quickly if you know if the A and B, if you can see if they're positive or negative. So you'll need the 4 pictures here. Right, the first one is easy. It's like the one I just did. If A is positive and B is positive, the graph will increase exponentially like this, and this point here will be 1. Okay? The next one, if the A is negative and the B is positive, it looks similar but just upside down. And again, this is 1. If the A is positive and the B is negative, does anybody know how that one's different?
Should be from the other side.
Stop us.
Yeah, it's flipped around this way, isn't it? So it'll be decaying. And here is, again, 1. And the last one, A is negative, so it's upside down, and B is negative, so it's decaying. So it'll be like this. And this x-axis is an asymptote, meaning the graph never reaches the x-axis and certainly doesn't cross it in these 4 graphs. So you'll need to copy these in your notebook.
What's the time?
Oh yeah, for this picture it's 31. So I think it's good in the exam, they do like you to mark off that this is the number 1.
So it's always 1 and minus 1.
Oh yeah, obviously. Sorry, what am I doing? -1. You know, regardless of the value of A and B, it always crosses. Oh no! I said an untruth. That's not 1. Dirty liar. What is it?
What?
No. Oh no. Angela will tell you why it's not that. Does that look like, could it ever be -1?
That's not 1.
No, it's not 1. I spoke an untruth. What is it? No, you're getting desperate now. No, think about it. What is it? It's A. Because if you put x as 0, you have e power 0, which is 1, times A. So that's an A. This one here, that's A, that's A, and that's A. Well, the minus is already in the A, so I won't write it again. Yeah. Yeah. Well, through those? Yep. Not yet. So you describe this as exponential growth, and this one would be exponential. I guess it is kind of like a growth as well, but this one is like decay, and this one is like decay. The reason being because it's like shrinking to the x-axis, whereas in the first two it's growing away from the x-axis.
So it's not based on the slope?
No, it is, but it's what the slope is doing. So here the slope is getting bigger. The slope is getting bigger in size, even though it's negative. Here it's flattening, and here it's flattening. Yeah?
So although in the last one, the bottom right,
Yeah.
so although the slope is positive, it's still decaying?
Yeah. So the decay, the description, the word decay, it has this meaning when you put it with the word exponential. So exponential decay just means that the graph is very quickly leveling off. regardless of the slope being positive or negative. The key thing here is that it's flattening out.
Is there any chance that it goes, it eases towards the, instead of moving towards the x-axis for the growth and the decay, moving towards the y-axis, what would that equation be?
That's actually more like what the log looks like, which is what we'll do. So you can't, the log graph looks like it's decaying to the y-axis. Yeah, that's actually what the log graph is, so that'll be in a later lesson. Yeah, there is another graph that's like this but kind of looks like it's flipped, and that's actually the log. Yeah.
Isn't that,
Yeah, go ahead, Joe.
yeah, isn't that also similar to the way rational looks like? It looks like this.
The 1 over x?
Yeah.
Or the root x, yeah. Yeah. They have a similar shape, don't they?
Yeah.
The only difference is, though, with the square root, I think it hits the axis, because you can have a root of 0.
Just rational. 1 over x within.
Oh, yeah, so it's the same thing. It shoots down, decays to the...
That's it. So that's decay, yeah?
You could describe that as decay, but usually the word decay is used in the context of E. Yeah. You'd see this in biology as well. You know, you'd say exponentially growing or exponentially decaying.
We actually just did that last.
And in physics too, yeah. What? Yeah. Yeah. And what did you say you did in biology where you used this?
Last tutorial we took about exponential graphs.
Oh, really? That's good timing then. So were they similar to this?
Yeah.
In your biology?
I think it's.
But did Colin show you the other one where it's like if I scroll down, this one. So it's flat. Then it goes up like this. Then it levels off.
Yeah.
So here you would describe it as being constant, and here it would be constant as well. And then here, this is exponentially growing, and this is exponentially decaying, and in the middle here is linear. So this one is a bit like a decay here exponentially, and this one is a bit like an exponential growth then. Yeah. Did Colin give you a name of this graph? Because you can't really call it exponential because... Yeah, very good, okay. Because it's actually changing its behavior. It's going from constant exponential growth, linear exponential decay, and constant then. And again, it's a very common graph in biology because you can... sigmoid, yeah. Or in maths, I think it's called logit as well. Yeah. Anyway, that's good that Colin did this one in biology. Okay, so what I want you to do now to get started on, I think A and B in each question. A and B. Yeah. Yes, I was going to reply. I didn't have time. So it's Moodle quiz. No. It's Moodle quiz. You type the answer in. Yeah.
I tried to change the contract.
But I'll give you paper to work on. But the good thing is, one sec. No. It's only typing like, if I said solve for x, you just have to literally type 2, 3, whatever the answers are. Yeah, just a... No. And the other thing is, I'll let you do the quiz twice, and after you do it the first time, you'll see which ones are right and wrong. So then I'll let you try it again. You can keep the right answers, and then the ones that are wrong, you can rework them out. And then I think I'll take your highest of the 2 marks or something like that. Yeah. So you get 2 shots at the quiz in the 2-hour period. Yeah. Okay, what's your question? Actually, let me stop this video here.
Is it like starts from a certain point and then goes to infinity?
No, it actually is coming out from the x-axis. Yeah.
Yeah, so it's like this.
Okay, yeah. If you want. Yeah.